Hello, and welcome to Computing Fundamentals 2. Today we are going to discuss isomorphism. In this video, I will focus on the applications of isomorphism and how it is employed in real application. Then I will discuss the formal definition of isomorphism and I will explain bijective, injective, and surjective functions. After that, I will give a few examples about isomorphism. Then we will do an activity to determine whether two graphs are isomorphic or not. At the end, I have an interesting game for you to play to check whether two graphs are isomorphic or not. You need to know whether it is possible to draw two graphs in the same way. That is, do the graphs have the same structure when we ignore the identities of their vertices? For example, all smart mobile devices have a fingerprint scanner, what is so-called Touch ID. One possible way to perform such Touch ID identification is to use a graph isomorphism to compare the fingerprints of the user. That's why the device asks the user to give as much as possible fingerprints from different angles. Chemistry graphs are used to model chemical compounds. Different compounds can have the same molecular formula but can differ in structure. Such compounds can be represented by graphs that cannot be drawn in the same way. The graphs representing previously known compounds can be compared with a newly discovered compound to check whether it is something we discovered before or not. So now let us take a formal definition of isomorphism. The symbol graphs G1 and G2 are isomorphic if there exists a one-to-one and onto function f from V1 to V2 with the property that A and B are adjacent in G1 if and only if it preserves adjacency and non-adjacency. Such a function f is called an isomorphism. That was the mathematical definition of isomorphism. In other words, when two symbol graphs are isomorphic, there is a one-to-one correspondence between vertices of the two graphs that preserves the adjacency relationship. Isomorphism of symbol graphs is an equivalence relation. So what we understand from the previous definition that isomorphism could be established if we have one-to-one and onto function between graphs G1 and G2, and we know that function is called bijection. Bijection, what do we mean by bijection? Okay, I will explain now. If you map U1 to V1 and U2 to V4 and U3 to V3 and U4 to V2, this type of mapping is called bijection. Now let us take a formal definition of bijection. To simplify this, we can define a bijection or a bijective function or a one-to-one correspondence is a function between the elements of the two sets, where each element of one set is paired with exactly one element of the other set, and each element of the other set is paired with exactly one element of the first set. There are no unpaired elements in bijective function. So a bijection is a map from a set A to a set B. To be more specific, it is a map between the elements of set A to the elements of set B. That is a one-to-one injection and onto, which is a surjection. So you might be saying now, I don't know what a bijection is. And now you are telling me a bijection is when we have a function which is an injection and a surjection at the same time. A one-to-one correspondence between elements of set X and set Y. You will see in the figure that Adams is mapped to A, Chow is mapped to C, Goodfriend is mapped to B, now Rodriguez is mapped to A, Stevens is mapped to F. Now you will notice that D, the element in the set Y, has not been mapped by any element from the set X. So we can call this function one-to-one, but it is not an onto function. Another example. If we have the elements of the set X and the set Y, Now A is mapped to 3, B is mapped to 2, C is mapped to 1, D is mapped to 3 again. Now all elements in the set Y, but in this case A and D in the set X has been mapped to the same element in Y. So this is not a one-to-one function, but it is an onto function. More example. The figure is showing different types of mapping function between the elements of set X and set Y. In figure A, we have all elements of X are mapped to an element of Y in one-to-one. This means there is no two elements in X mapped to the same element in Y, so this is a one-to-one function. In figure B, all elements in set Y are mapped by an element from the set X, and there is no two elements of Y mapped to the same element of X, so this is an onto function. In figure C, each element of the set X is paired exactly with one element of the set Y, and each element of Y is paired with exactly one element from the set X. There are no unpaired elements, so this is a one-to-one and onto function at the same time, and we call it a bijection. Try to find why figure C has neither one-to-one or onto function. Look for unpaired element or elements, or look for an element mapped more than once to an element from the other set. Now, how we could determine whether a pair of graphs like G and H are isomorphic? So we can use the following checklist. Two simple graphs are isomorphic if and only if there is a bijection function between f of u and f of v. Look to the mapping. u1 is mapped to v1, u2 is mapped to v4, u3 is mapped to v3, and u4 is mapped to v2. So all elements are paired with one distinct element from the set V, so it passes our first check. Is the number of vertices on both graphs the same? So G has 4 vertices and H has 4 vertices, so it passes the second check. Does both graphs G and H have the same number of edges? Both have 4 edges, so it passes the third check. Is there a structural similarity? So the adjacent vertices in G are mapped to adjacent vertices in H. If you look to the diagram, U1 has been mapped to V1. Now V1 is adjacent to V4 and V3. You will see now V4 is mapped to the vertex U2 and V3 is mapped to U3. Now U2 and U3 are adjacent to U1. So we have now preserved the adjacency and non-adjacency between two graphs, so we could conclude that those two graphs are isomorphic. A simple activity for you to do, I want you to determine whether each of these functions is a bijection. You can come back to the video and check the answer. Actually, the function 2x plus 1 is a bijection. X to the power 2 plus 1 is not a bijection. X to the power 3 is a bijection. And x to the power 2 plus 1 divided by x to the power 2 plus 2 is not a bijection. You can use Sage to verify your answer. Let us take an example. Show that the graphs displayed in figure 9 are not isomorphic. Now, you will find that both G and H have 5 vertices and 6 edges. However, H has a vertex of degree 1, namely E. If you look to the vertex E, you will find it has a degree of 1, whereas G has no vertices of degree 1. There is no vertex in G with the degree 1. So this is dissimilarity, a concrete difference between H and G. It follows that G and H are not isomorphic. A second example. Determine whether the graphs shown in figure 10 are isomorphic. You will find that both graphs have 8 vertices and 10 edges. They also both have 4 vertices of degree 2 and 4 vertices of degree 3. However, G and H are not isomorphic. I will explain why. The graph G and H both have 8 vertices and 10 edges. They also have 4 vertices of degree 2 and 4 of degree 3. Because these invariants all agree, it is still conceivable that these graphs are isomorphic. However, G and H are not isomorphic. To see this, note that because degree of A equal 2 in G, A must correspond to either T, U, X, or Y in H, because these are the vertices of degree 2 in H. However, each of these 4 vertices in H is adjacent to another vertex of degree 2 in H, which is not true for A in G. You can simply see now they are mapped to a vertex with degree 2, but they are adjacent to a vertex with degree 3. Another way to see that G and H are not isomorphic is to know that the subgraphs of G and H made up of vertices of degree 3 and the edges connecting them must be isomorphic. If these two graphs are isomorphic, and the viewer can verify this, however, these subgraphs shown in the figure are not isomorphic. Another example. Determine whether these two graphs are isomorphic. Both G and H have 6 vertices and 7 edges. Both have 4 vertices of degree 2 and 2 vertices of degree 3. It is also easy to see that the subgraphs of G and H consisting of all vertices of degree 2 and the edges connecting them are isomorphic. Because G and H agree with respect to these invariants, we could find now a function f to preserve adjacency and non-adjacency and to find out whether they are isomorphic or not. We will now define a function f and then determine whether it is an isomorphic. Because degree of u1 equal 2 and because u1 is not adjacent to any other vertex of degree 2, the image of u1 must be either v4 or v6. The only vertices of degree 2 in H not adjacent to a vertex of degree 2. We set f of u1 to be v6. If we found that these choices do not lead us to isomorphism, we would then try f of u equal 4. Because u2 is adjacent to u1, the possible image of u2 are v3 and v5. We set now f of u2 to be equal to v3. Continuing in this way, using adjacency of vertices and degrees as a guide, we set f where we have f of u3 equal v4, f of u4 equal v5, f of u5 equal v1, and f of u6 equals to v2. We now have a one-to-one correspondence between the vertex set of G and the vertex set of H, namely f of u1 equal f v6, f of u2 equal v3, f of u3 equal v4, and f of u4 equals v5, and f of u5 equals v1. Now f of u6 is equal to v2. We examine the adjacency matrix of G and the adjacency matrix of H with the rows and columns labeled by the images of the corresponding vertices in G. You see now from the adjacency matrix that the adjacency matrix of G equals the adjacency matrix of H. It follows that F preserves edges, so G and H are isomorphic. Now you need to note that if F turned out not to be an isomorphism, we would not have established that G and H are not isomorphic, because another correspondence of the vertices in G and H may be an isomorphism. It is often difficult to determine whether two simple graphs are isomorphic. There are n factorial possible one-to-one correspondence between the vertex set of two simple graphs with n vertices. Testing each such correspondence to see whether it preserves adjacency and non-adjacency is impractical if n, the number of vertices, is at all large. Sometimes it is not hard to show that two graphs are not isomorphic. In particular, we can show that two graphs are not isomorphic if we can find a property only one of the two graphs has, but that is preserved by isomorphism. A property preserved by isomorphism of graphs is called a graph invariant. For instance, isomorphic simple graphs must have the same number of vertices because there is a one-to-one correspondence between the sets of vertices of the graphs. Now you can do this simple activity to judge whether graph G and the graph H are isomorphic. You will notice now both have the same number of vertices, both have the same number of edges, so we can simply say yes, they are isomorphic. In the second example, those two graphs have the same number of vertices. Graph G has 5 vertices and the graph H has 5 vertices as well. The number of edges equal in both graphs, and there is no difference in their structure, so we can simply say yes, they are isomorphic. Now in the last example, yes, they are isomorphic because we have the same number of vertices, the same number of edges, and also we have and preserve adjacency and non-adjacency between the two graphs. So yes, they are isomorphic. Isomorphic simple graphs must have the same number of vertices because there is a one-to-one correspondence between the sets of vertices of the graphs. Isomorphic simple graphs also must have the same number of edges because the one-to-one correspondence between vertices establishes a one-to-one correspondence between edges. In addition, the degrees of the vertices in isomorphic simple graphs must be the same. That is, a vertex v of degree d in G must correspond to a vertex f of v of degree d in H, because a vertex w in G is adjacent to v if and only if f of v and f of w are adjacent in H. Finally, in this link you will find an interesting game to play to check whether two graphs are isomorphic or not. Enjoy doing this, and thank you for watching this video, and see you in the next one.